Over the last 20 years or so, vinyl records have made a remarkable comeback, with global sales on new vinyls of around 80 million units in 2023 and more than CDs. Digital music downloads and streaming still outweigh vinyl and CDs by a huge margin, and that isn't going to change. However, some fantastic music has and is being released on vinyl. Hi-Fi magazines are awash with turntable and cartridge reviews, and complete turntables with integrated moving magnet phono EQ preamps start for as little as £180 or $220 and range all the way up to very high-end units retailing at hundreds of thousands, and that's before you've added a cartridge and a phono amplifier. But the question is, what does it take to get you to say 95% of the full potential performance of an LP? Remember that a good LP has a signal-to-noise ratio of around 50 to 60 dB and a dynamic range of not more than 60 dB. This video will explain the basics of vinyl reproduction and attempt to answer that question with a little bit of history thrown in for good measure. The machine shown here is used to cut the acetate master from which, after further processing, the production vinyls will be pressed. Most of the major engineering challenges of equalization, pressing, and then extracting the sound encoded on an LP's grooves were solved in the early 1950s when the RIAA standard was proposed. Those challenges were primarily triggered by the requirement to increase the playing time of a record, which meant the grooves had to be much finer than the old 78 RPM shellac records. This in turn meant record wear and noise became serious issues, while on the pickup side, finer styluses and lower tracking weights were required. So the engineering challenges in the late 1940s and early 1950s to achieve longer LP record playing time with improved fidelity were very significant. It took 8 to 10 years for the RIAA standard to be adopted industry-wide. Prior to this, numerous EQ standards caused some consternation for consumers who have had to set the EQ parameters on their gear to match that specified by the music company that had pressed the vinyl. Examples would have been Decca, Columbia, RCA, and even the BBC here in the UK had its own standard. Consumer turntables and pickup arms for the most part were acceptable but not great compared to modern ones, and really only came of age in the early 1970s, epitomized by the Linsondic LP12, still held in awe by audiophiles. In 2024, a good second-hand exemplar will regularly fetch over £1,000 on eBay, 45 years after they first appeared, and in 2012, a limited series of 40 units was issued by Lin to mark the LP12's 40th anniversary, with plinths made from Highland whiskey cask oak that retailed at $25,000 apiece. The specific refurbished Linsondic shown here was up on eBay for over £2,000. However, advances in CAD/CAM, tighter manufacturing tolerance capabilities, and newer, more readily available materials, e.g. carbon fiber, Teflon, and modern acrylics and plastics, mean that contemporary turntables are streets ahead of the turntables available in the 1940s and 1950s. The original project debut turntable shown here first retailed for £120 in the UK in the late 1990s, and is a good example of the kind of performance one could get for the money from a modern product. Let's move on now to talk a bit about the technicalities of vinyl reproduction. The image above is that of a swept sine wave, which will be used to explain how a velocity transducer, which is what a phono pickup is, works and why equalization is needed in the first place. The first thing to consider is that a phono pickup in essence consists of a coil and a magnet that are magnetically coupled. If you move the one with respect to the other, a voltage is generated in the coil. In moving magnet types, the magnet is fixed with respect to the coil, which is fixed into the cartridge shell, and in moving coil types, the magnet is fixed in the shell and the coil is moved by the stylus deflections arising from the record groove. At low frequencies, the line AB shows the slope of the sine wave from peak to peak. This slope represents the maximum rate of change of the signal at that frequency. Line CD shows the rate of change or slope at HF. It's quite easy to see that the rate of change at HF is much higher than that at LF because the slope is steeper. Faraday's law of induction states that the output voltage of a coil is proportional to the rate of change of flux cutting the coil. Or restated, the faster a coil moves through a magnetic field of given flux density, the higher the output voltage. Exactly the same principle applies if a magnet is moved with respect to the coil. Regarding a phono pickup, this means the faster a stylus is deflected, the higher the output voltage. The output increase in voltage is directly proportional to frequency at a rate of 6 dB per octave or 20 dB per decade. This means that if the stylus deflections were fixed at, say, 0.05 millimeters, and a 200 Hz signal and then a 2 kHz signal recorded on a vinyl, the output at 2 kHz would be 10 times the value at 200 Hz before equalization. So if a constant voltage output versus frequency is required, the physical amplitude of the grooves has to decrease by the same amount that the voltage amplitude output from the cartridge increases due to Faraday's law. However, applying this minus 20 dB per decade across the whole audio band from 20 Hz to 20 kHz is not practical because, if adopted, would lead to a number of serious technical problems. Firstly, on the cutting edge side, with constant velocity grooves, the physical amplitude modulations, i.e. music information at HF, would be too small to track accurately and further buried in the disc's noise. Additionally, it is unlikely that because of these modulations would be so small, they would easily be damaged by the pickup, resulting in a loss of HF information. This, by the way, was a fundamental problem with the old heavy pickups from the 1930s through to the 1950s. An example is shown here, and one of the reasons the signal bandwidth was limited to about 6 kHz. Further, if the grooves were indeed cut at constant amplitude across the whole audio band, the gain range, and indeed, as already intimated, the modulation range of the grooves itself, would cover 3 decades or 60 dB. Such high gain and physical modulation ranges on the media invite noise problems at HF and issues with LF content related to record warp and arm resonance at the lower end. What if we just cut the disc flat, i.e. the same physical deflection at LF and HF, and then EQ'd it with a single minus 20 dB per decade low-pass filter set at 20 Hz? With this approach, the stylus would not be able to track the groove at HF, and there would be serious problems trying to cut a master under this regime. Clearly, some trade-offs and a smarter approach are required. In this depiction of the RIAA EQ recording and playback process, the purple line represents the signal level response over the audio band from the cartridge before equalization. The red line is the equalization amplifier response, and the green line is the output of the equalization amplifier. The solution to the technical dilemma mentioned a few moments ago was to split the frequency band into 4 sections and then, with respect to the physical deflection on the groove, cut the master using a combination of constant velocity and constant amplitude as defined by the frequency bands. The blue shaded area is the first band up to 50.05 Hz. The frequencies defining the bands are called the breakpoint frequencies, and the breakpoint frequencies being shown here are for the RIAA standard. The second band covers 50.05 Hz to 500.05 Hz. The third band covers 500.5 Hz through to 2.12 kHz and is commonly called the midband. And finally, the upper band, or the HF area or region, covers everything above 2.12 kHz. We usually take the audio band as 20 Hz to 20 kHz, but as we will see a bit later, RIAA EQ should still be providing a minus 20 dB per decade slope well above the audio band. In other words, EQ doesn't suddenly end at 20 kHz. As already mentioned, prior to the RIAA standard, there were a number of specifications because the frequency breakpoints chosen by the different vinyl producers were different. The RIAA standard, which is what we're showing here, emerged in 1954. This split the recording equalization and therefore playback equalization into the 4 sections I've just described, consisting on the playback side of 2 pole frequencies at 50.05 Hz and 2.12 kHz and a 0 at 500.5 Hz. It should be noted that it took about 5 years of toing and froing within the industry to settle on the RIAA spec, and at least another 8 to 10 years before it became embedded as the industry standard. This was not something that emerged from 1 or 2 meetings of engineers. From 50.05 Hz to 500.5 Hz, the record groove is cut at constant amplitude versus frequency, which means the velocity-derived voltage signal on the pickup side increases at plus 20 dB per decade, starting at 50.05 Hz and going up in frequency to 500.5 Hz. The midband, 500.5 Hz to 2.12 kHz, is cut at constant velocity, which means that the physical deflection of the groove on the disc has to decrease at minus 20 dB per decade, from 500.5 Hz to 2.12 kHz, yielding a constant amplitude output from the pickup. Above 2.12 kHz, the groove modulation returns to constant amplitude, so the output from the pickup cartridge rises with respect to the midband at plus 20 dB per decade. The red traces the playback EQ amp response versus frequency. Going up in frequency from 50.05 Hz to 500.5 Hz, the gain decreases at minus 20 dB per decade. In the midband, where the gain is typically 35 to 40 dB, reference the input signal from the cartridge, the gain versus frequency response is flat. Above 2.12 kHz, the gain slopes off again at minus 20 dB per decade, and this continues all the way up to HF until the amplifier response equals 0 dB, where it flattens out. The green line is the output response of the EQ amplifier and is as good as flat to within 0.2 dB from 20 Hz to 20 kHz in a well-designed phono amplifier. On the EQ amplifier, there is a further breakpoint at 20 Hz, shown by the red arrow, added as an amendment in the early 1960s in an attempt to address low-frequency motor rumble and arm resonance, which is usually around 8 to 10 Hz. In addition, it also offered some attenuation of record warp, which is evident between 1.8 Hz and 3 or 4 Hz. This was rejected by many practitioners for reasons discussed in the stereophile article you can link to in the comments section below. The slope below 20 Hz would normally be set at minus 20 dB and derived with a simple RC network setting the lower minus 3 dB cutoff at 20 Hz and probably not quite enough to curtail rumble and arm resonance sufficiently. Many modern designs, including some of mine, use a high-pass minus 40 dB per decade rumble filter that really does take care of the issues just mentioned. However, it should also be noted that most modern turntables, even reasonably priced ones, don't suffer from anywhere near the issues evident on the consumer products of yesteryear, thanks to modern manufacturing capability and improved materials. The red arrow here shows an HF pole somewhere up at 40 or 50 kHz. This has nothing to do with the 50 kHz Neumann pole story circulating around in the DIY community. It's just there to show that the groove modulation drops off at HF because the source signal and the cutting head amplifiers are bandwidth limited. Again, more information in the stereophile article. There is no Neumann pole, and there's no useful information in any recording above 40 or 50 kHz, let alone 20 or 25 kHz. There are some old test records and measurements that show HF energy on cymbal crashes of up to 50 kHz of plus 2 dB reference to 1 kHz level, but whether this is actually music energy or some non-program artifact is not clear. You can read about this in the Tomlinson-Holman articles that I'll link to in the comments section below. Some people have proposed the difference in sound between 16-bit 44 kHz CD, which has a steep brick wall filter at 22 kHz, and vinyl might be down to intermodulation of whatever remnant music energy remains on vinyl recordings above 20 kHz, folding harmonics down into the audible band, but there are no definitive investigations into this as far as I know. The response above 40 or 50 kHz should gently drop off at 20 dB per decade as shown with the dashed green line. In any event, a natural zero will occur at HF due to the amplifier gain response, which in the non-inverting configuration used almost exclusively in RIAA EQ amps for reasons of thermal noise cannot be less than 0 dB. However, active-passive topologies and all-active EQ schemes that use secondary post-low-pass filtering largely overcome this pitfall. It turns out the equalization requirements on the pickup side also help in terms of HF noise caused by both the pickup amplifier and surface noise on the record itself. This was no accident in the specification and deliberately done to improve the overall system signal-to-noise ratio. Because the output above 2.12 kHz is attenuated at minus 20 dB per decade with respect to the midband to cater for the plus 20 dB per decade equalization preemphasis of the groove deflections, any amplifier and record surface HF noise will also be attenuated by the same amount since these are not RIAA encoded. The result is an altogether quieter record pickup amplifier system. At the low end of the spectrum, below 500 Hz, the signal is boosted, and there we do have to be careful about hum ingress. But this is a relatively easy problem to solve with good construction techniques, layout, and wiring. And that, in short, is how the RIAA equalization, recording, and playback chains work in perfect harmony to get the sound out of your speakers. That an electromechanical system with tiny pickup signals of around 5 millivolts at 1 kHz in a moving magnet system, or 1/10 of that in a moving coil system, at 1 kHz and some serious equalization on both the recorder and playback chains work so well is to my mind an engineering marvel. And work well it does. If you're used to the perfect sound forever of CDs and digital music sources and not familiar with records, you will certainly be impressed with the sound of a good vinyl system, and especially so after considering some of the technical challenges presented in this video. As pointed out by others in the field, the final RIAA EQ standard was very, very well thought through across a wide range of technical aspects, and the fact that it quickly became adopted as an international standard and is still used today is testament to this. For a more in-depth look at the subject and the history, Gary A. Gallo's Disc Recording Equalization Demystified, linked to in the comments section below, is a wonderful reference. That's it for this quick introduction to RIAA equalization. If you liked the video, give it a thumbs up and feel free to share the link. And don't forget to visit hifisonics.com. Thank you.